In the endless silent theatre of the cosmos, the vast majority of stars are not the brilliant solitary titans that dominate our night sky. They are the quiet ones, the unassuming, diminutive red dwarfs. Billions upon billions of them populate the Milky Way, a silent, unseen majority, their faint ruddy light, a mere whisper against the roaring symphony of their larger cousins. For decades, we imagined them as tranquil harbours for life, their lifespans stretching into the trillions of years, offering near infinite time for biology to take root and flourish on orbiting worlds. We envisioned planets bathed in a perpetual gentle twilight, stable and serene cradles for existence. This was the galaxy we hoped for, a galaxy filled with quiet, peaceful neighbourhoods. But the universe has a violent heart, and the quietest corners often hide the most ferocious tempers. From the depths of space, a signal arrived. A faint, almost imperceptible flicker from a distant star, followed by a ghostly shadow. It was a message written in plasma and magnetic fury, a story of an eruption so colossal it defies earthly comparison. For the first time, we have witnessed it directly, a star light years away unleashing a coronal mass ejection, a stellar hurricane of charged particles. And this confirmation, this single groundbreaking observation, has transformed our understanding of the cosmos. It suggests that these supposedly placid red dwarf systems may not be gentle harbours at all. They might be cosmic shooting ranges where planets in the habitable zone are periodically scoured clean by blasts of unimaginable power. The silent majority has found its voice, and it is screaming. Our quest to understand this stellar violence began not in the dim glow of a red dwarf, but under the familiar light of a star, much like our own Sunday. It is a young, energetic star, a celestial adolescent named E.K. Draconis, located about 111 light-years from Earth, in the northern constellation of Draco the Dragon. To the human eye, it is just another faint pinpoint of light, unremarkable among its countless peers. But to the patient, unblinking gaze of our observatories, this star was a perfect laboratory. A team of astronomers led by Kosuke Namekata and Yuta Notsu from Kyoto University dedicated themselves to observing this solar twin. They were stellar detectives hunting for clues not of a crime but of a fundamental cosmic process they were certain must exist beyond our solar system. Their logic was sound. If our own star, a relatively stable middle-aged G-type star, can produce these spectacular eruptions, then surely other stars must do the same. Yet seeing it is another matter entirely. Imagine trying to spot a puff of smoke from a campfire on a distant mountain, when the mountain itself is already just a speck on the horizon. This was the scale of their challenge. A coronal mass ejection, a CME, is not a flash of light like a stellar flare. It is a cloud. A colossal semi-transparent bubble of magnetized gas of plasma expanding outwards into the void. Against the overwhelming glare of the star itself, this ghostly eruption is all but invisible. The team knew they couldn't just take a simple picture. They needed a more clever, more subtle technique. Their method relied on a deep understanding of light and motion, a principle discovered in the 19th century by Christian Doppler. Think of the sound of an approaching ambulance. As it rushes towards you, the siren's pitch sounds higher. As it speeds away, the pitch drops. The sound waves are being compressed as the ambulance approaches and stretched as it recedes. Light behaves in precisely the same way. When an object moves towards us, its light waves are compressed, shifting them towards the blue end of the spectrum. This is a blue shift. When it moves away, its light waves are stretched, shifting them towards the red end of the spectrum, a red shift. The astronomers aimed their instruments at E.K. Draconis not to take a picture, but to analyze its light, to break it down into a rainbow of constituent colors, a spectrum. They were looking for a very specific signature. First, they anticipated a flare, a sudden, brilliant flash of energy marking the moment of magnetic reconnection on the star's surface. This would be the muzzle flash of the cosmic cannon. Then they would watch for the cannonball. As the enormous cloud of plasma, the CME, erupted from the star's surface and billowed towards Earth, its leading edge would be moving towards our telescopes. The light from that specific part of the stellar atmosphere, the part heaving outwards, should be dramatically blue-shifted. After months of patient observation, using both NASA's Transiting Exoplanet Survey satellite TESS and ground-based observatories in Japan, their moment arrived. E.K. Draconis flickered. A powerful superflare 30 times more energetic than the most extreme flares ever recorded from our own sun lit up their sensors. This was the flash. The team held its breath. Minutes later, the spectral data began to stream in, and there it was. A huge distinct signature of hydrogen atoms, not stationary but moving. And they were moving fast. The data showed a massive quantity of gas hurtling outwards, its light unmistakably blue-shifted, indicating a velocity of over 1 million miles per hour. It was a ghostly fingerprint left by a plasma projectile of almost unimaginable scale. The mass of the ejected cloud was staggering, more than 10 times larger than any CME ever witnessed, erupting from our own Sunday. This was no puff of smoke. It was a stellar tsunami, a gaseous continent tearing itself free from its parent star and surging into interstellar space. The evidence was undeniable. The chain of events was complete. For the first time in human history, we had recorded the complete sequence of a coronal mass ejection from a distant alien star. The discovery sent ripples through the astronomical community. It was a triumphant validation of decades of theory, a technical masterpiece of observation. But to truly grasp the monumental power we have just witnessed, we must first return home to our own star and understand the beast that slumbers at the center of our solar system. The Sun, our life-giving parent, is a sphere of incandescent plasma, a chaotic ball of magnetic fields twisted into unimaginable complexity by its own rotation and convection. Picture the Sun's surface not as a smooth, placid ocean of light, but as a turbulent, boiling sea. Great loops of magnetic energy thousands of miles high arch into the corona, the Sun's ethereal outer atmosphere. These magnetic field lines are like cosmic rubber bands. For weeks, sometimes months, the churning motion of the Sun's interior twists these bands tighter and tighter. Energy, incomprehensible amounts of it, is stored within these magnetic structures. More energy than humanity has produced in its entire history. The tension builds day by day, hour by hour, reaching a point of instability, a tipping point from which there is no return. Then, in a fraction of a second, the rubber bands snap. The process is called magnetic reconnection. The field lines break and violently reconfigure themselves into a simpler, lower energy state. The stored energy is released in a blinding flash of radiation, a solar flare, but often this is not the end of the event. The reconfiguration of the magnetic field can act like a cosmic slingshot, launching the plasma that was trapped within the magnetic loops out into space. This is the coronal mass ejection. 1 billion tons of protons and electrons, a cloud of superheated gas larger than the Earth, is unleashed from the Sunday. It travels at millions of miles per hour, a relentless solar wind that sweeps through the planets. For most of its existence, humanity was blissfully unaware of this celestial threat. We saw the Sun as a symbol of constancy, a perfect, unchanging orb. That perception was shattered on the 1st of September 1859. Richard Carrington, an English amateur astronomer, was in his private observatory meticulously sketching a group of enormous sunspots. Suddenly, he witnessed 2 patches of intensely brilliant white light erupt from the sunspots. The flare lasted only 5 minutes. Carrington, initially baffled, knew he had seen something extraordinary. He had witnessed a white light solar flare, a rare and intensely powerful event. What he could not have known was what happened next. The flare was the flash, but the CME was the bullet, and it was now hurtling directly towards Earth. Just over 17 hours later it struck. The Earth's magnetosphere, our planetary shield, was overwhelmed. In the dead of night, the skies erupted in light. Auroras, the northern and southern lights, were seen all over the planet. They were so bright that people in the Rocky Mountains woke up believing it was dawn. Newspapers could be read by their eerie dancing light in cities as far south as Cuba and Hawaii. But this was more than a light show. The CME induced massive electrical currents in the nascent technological nervous system of the planet. Telegraph systems across Europe and North America went haywire. Pylons threw sparks. Operators received electric shocks. Some disconnected their batteries only to find that the auroral currents alone were strong enough to power their machines, allowing them to send and receive messages. Paper in the telegraph offices spontaneously caught fire. It was a world teetering on the edge of a new kind of natural disaster. In 1859, the damage was novel and contained. Now imagine a Carrington-level event striking our modern world. Our civilization is a fragile web woven from electricity and information, utterly dependent on a global network of satellites, power grids, and communication systems. A direct hit from a powerful CME would be a civilization-altering catastrophe. Satellites in orbit, the backbone of GPS banking and global communications, would be fried by charged particles, becoming a cloud of dead metal. The power grids on the ground would experience surges of current that would blow out transformers, massive custom-built pieces of equipment that take months or years to replace. Large swathes of our planet could be plunged into darkness, not for hours or days, but for weeks, months, or even longer. The intricate dance of global supply chains would cease. The digital world would be silenced. We would be thrown back into a pre-electrical age, but without the skills to survive in it. This is the power of our own relatively placid star, and now we have confirmed that another star, EK Draconis, can produce CMEs 10 times more massive. This discovery is a chilling prelude, a warning shot, because as terrifying as the outbursts of sun-like stars can be, they may be dwarfed by the fury of the galaxy's most common residents, the red dwarfs. These small, dim stars make up nearly 80% of the stellar population of the Milky Way. If you were to select a star at random, chances are overwhelming that it would be one of these faint red embers. For astrobiologists, they have long represented a tantalizing paradox. On one hand, their sheer numbers and their incredible longevity lasting for trillions of years suggest they could be the most common sites of life in the universe. There are billions of them in our galaxy alone, and we now know that many of them host rocky Earth-sized planets. But there is a critical catch. Because red dwarfs are so much cooler and dimmer than our Sun, their habitable zone, the orbital region where liquid water could exist on a planet's surface, is incredibly close to the star. A planet in a red dwarf's habitable zone would be orbiting far closer than Mercury orbits our Sunday. This proximity creates a host of problems. The planet would likely be tidally locked, with one hemisphere locked in perpetual scorching daylight and the other in an endless frozen night. Life, if it existed, might be confined to a narrow sliver of twilight between these two extremes, the Terminator zone. But the gravest danger comes from the star itself. Red dwarfs, especially when they are young, are notoriously volatile. They are known to produce stellar flares that can be hundreds or thousands of times more powerful relative to their size than anything our Sun produces. We have seen these flares, we have measured their shocking intensity, but until now, the question of their CMEs has been a dark, unanswered variable in the equation for life. The discovery at EK Draconis provides the crucial, terrifying missing piece of the puzzle. It proves that powerful flares on stars are indeed accompanied by massive CMEs. Now we must apply that knowledge to the red dwarf scenario. Imagine a planet tidally locked, huddled close to its parent star for warmth. And then imagine that star not a distant benevolent sun, but a moody, furious neighbour, unleashing a plasma storm 10 times more powerful than the Carrington event. Because the planet is so close, the CME would strike not in 17 hours, but perhaps in only 1 or 2. There is no time for the planet's magnetic shield, if it even has one, to respond. The impact would be cataclysmic. It would be a point-blank blast from a cosmic shotgun. The CME would slam into the planet's atmosphere with unimaginable force. Over thousands or even hundreds of years, these repeated impacts could strip the world of its air entirely, a process known as atmospheric erosion. The planet's water would be blasted into space or broken down into hydrogen and oxygen, lost forever. Any protective ozone layer would be annihilated, exposing the surface to a lethal dose of sterilizing ultraviolet radiation from the star's frequent flares. The very ground would be sputtered away by the relentless bombardment of high-energy particles. The gentle twilight haven we imagined becomes a radiation-blasted, airless desert, a world not just inhospitable, but actively hostile to the chemistry of life. This is the profound and sobering implication of this discovery. The most common real estate in the galaxy, the trillions of planets orbiting red dwarfs, might be systematically sterilized by their own parent stars. This raises one of the deepest and most unsettling questions in all of science, the Fermi paradox. In the 1950 seconds, the physicist Enrico Fermi famously asked, given the vastness of the universe and the high probability of other Earth-like planets, Where is everybody? The silence from the cosmos is deafening. We have pointed our radio telescopes at the heavens and have heard nothing but the static of the cosmic microwave background. Scientists have proposed many solutions to this paradox, many potential great filters. Perhaps life is incredibly rare. Perhaps intelligence is. Perhaps civilizations inevitably destroy themselves with their own technology. But now we have a new, compelling, and deeply pessimistic candidate for a great filter. Perhaps the universe is silent because the vast majority of planets that seem habitable are in fact located in stellar systems that are fundamentally lethal. Life may be common, but it is repeatedly, systematically, and violently scoured out of existence before it has a chance to evolve intelligence and technology. The galaxy could be filled with the ghosts of failed biospheres, worlds where life began in the brief, quiet interludes, only to be erased by the next stellar tantrum. Our existence on Earth orbiting a stable, well-behaved star at a safe, respectful distance might be an extraordinary exception, a stroke of cosmic luck on a galactic scale. Is there any hope? Could life find a way? The tenacity of life is legendary. On Earth, it thrives in the crushing pressures of the deep sea, in the boiling water of geothermal vents, in the acidic pools of volcanic craters. Perhaps life on a red dwarf planet could adapt to this violent environment. Maybe it would never emerge on the surface, evolving instead in the deep oceans shielded from the radiation by a thick layer of water or ice. Such a world would be a cradle and a prison, its inhabitants forever cut off from the starlight and the universe beyond. Or perhaps life could evolve underground, becoming a subterranean biosphere of chemotrophs, drawing energy not from starlight but from the planet's internal heat and chemical gradients. It's even possible that a planet could possess a magnetic field so powerful it could withstand the onslaught of even the most ferocious stellar CMEs. But these are for now merely hopeful speculations, flickering candles of optimism against a gathering storm of pessimistic data. The confirmation of the first extrasolar CME has opened a new chapter in our search for life. It has equipped us with a new tool and a new direction. We are no longer just planet hunters. We are now stellar weather forecasters for entire solar systems. With instruments like the James Webb Space Telescope, we can begin to study the atmospheres of these nearby exoplanets in detail. We can look for the telltale chemical signatures of atmospheric stripping. We can search for the presence of ozone, a key indicator of a planet's ability to shield its surface. We can now correlate our atmospheric observations with the observed flare and CME activity of the host star. Imagine a future observatory, a network of telescopes working in concert dedicated to this task. We witness a superflare on a nearby red dwarf Proxima Centauri, just 4 light-years away. We know it hosts at least one rocky planet, Proxima b, orbiting squarely in the habitable zone. Our system detects the flare, and then using the same Doppler technique, it confirms the launch of a massive CME. We calculate its trajectory. It is heading directly for Proxima b, and for the next hour we watch. We point our most powerful instruments at that faint, distant world, and we observe a planetary-scale cataclysm unfold in real time. We might see the planet's atmosphere light up with aurorae 1,000 times brighter than our own. We could detect the chemical composition of the atmosphere changing as it is torn away into space. We would be the first generation of humans to witness a planetary extinction event from afar. The experience would be profound, a humbling and terrifying glimpse into the raw, impersonal power of the universe. It would be a stark reminder of the delicate thread from which our own existence hangs. This journey of discovery began with a single flicker of light from a star named for a dragon. That flicker has illuminated a new and unsettling landscape in our cosmic backyard. It has forced us to reconsider our place in the universe, to re-evaluate where we might look for companions among the stars. The great bright stars that command our night sky are too short-lived to foster complex life. And now the small dim stars, the most numerous and long-lived, may be too violent. We seem to live in a narrow sliver of cosmic possibility, a galactic habitable zone that is constrained not just by location, but by the very temperament of the stars themselves. Our Sun, with its relatively gentle nature and predictable cycles, seems less an ordinary star and more an extraordinary sanctuary. The confirmation of an alien CME is not an ending. It is the beginning of a great and necessary recalibration of our search for life. It tells us that the universe is more complex, more dynamic, and perhaps more dangerous than we ever imagined. It compels us to look at our own sky with a renewed sense of wonder and a profound appreciation for the peace we so often take for granted. For we live under the steady gaze of a quiet star protected by a vast ocean of empty space and a shield of invisible magnetic force. We are the fortunate children of a calm sun, inhabitants of a tranquil island in a turbulent cosmic sea. And as we continue to peer into that sea, we must be prepared for the storms we may find and for the deep, unsettling silence that follows in their wake.